It's my extraordinary pleasure to introduce today's speaker, one of the most prolific and original young scholars I know, Dr. Niels Linnemann from the University of Geneva. Grüezi and bienvenue. Dr. Linnamann's research has focused on foundational and philosophical questions of spacetime theories, including, of late, the Ehlers-Pirani constructive axiomatics, theory generation and pursuit, especially in quantum gravity, and the laws of nature. On the continent, Dr. Linnemann has been exceptionally active in various outreach activities, such as organizing a regular workshop series that introduced young physicists to topics and methods of philosophy of physics. Beware the hemlock. From his impressively numerous publications, I'd like to draw your attention to the following ones. Together with Nick Huggett and Mark Schneider, Quantum Gravity in a Laboratory, a forthcoming Cambridge University Press monograph, an edited synthese volume on Eleanor Knox's spacetime functionalism, together with Karen Crowther and Chris Wüthrich, with contributions also from various Oxford scholars, then some publications such as Quantization as a Method of Generation, the Nature and Prospects of Theory Changes through Quantization in Studies, 2022. Non-empirical robustness arguments in quantum gravity, also published in Studies, 2020. In part in collaboration with Salim Iresh, Robert Michaels and Lisa Vogt, a series of papers on a unified account of laws of nature in the European Journal for the Philosophy of Science. Together with Rasmus Jaksland, Holography without holography, how to turn interrepresentational into intratheoretical relations in ADS-CFT, also in Studies. And together with Karen Crowther and Christian Wüthrich, what we cannot learn from analog experiments, published in Synthese. Dr. Linnemann did his undergraduate studies at the University of Münster and the University of Lund in Sweden. Afterwards, he moved to the UK for an MSc in philosophy of physics here at Oxford, and afterwards the the Part 3 Masters of Advanced Studies in Applied Mathematics at Cambridge the year after. In 2019, he earned his PhD at the University of Geneva in Switzerland with a thesis on philosophy of quantum gravity as a philosophy of discovery under the supervision of Christian Wüthrich, a thesis that was awarded the highest distinction avec félicitations du jury after a postdoc at the Rockefeller Institute at Western University and a position as an assistant at the University of Bremen. He is, since this spring, a senior research fellow in Professor Wüthrich's group, as well as a young academy fellow of the Hamburg Academy of Sciences. We're excited that today Dr. Linnemann will be speaking about one of his recent projects in collaboration with Chris Smink and Mark Baker, general relativity as a classical spin-2 field. Thank you very much, and merci vielmals for coming here today.
Yeah, thanks a lot, Patrick, for this kind words. Thanks a lot to you for attending this talk. Yeah, it's a great pleasure to finally stand on this side. As an MSc student, I also always attended the philosophy of physics seminar, and so it's just interesting to now, again, be on the other side here. The topic of the day will be the question how far one can think of general relativity as a classical spin-2 theory. This is joint work with Chris Smink and Mark Baker. We started working on this about 1.5 to 2 years ago when we were all together at the Rockefeller Institute. Mark is a physicist with a specific interest in energy momentum tensors, Noether theorems, and you will see how his specific interests also play out here. And I guess Chris Smink, you know, from our community. Good. Let's just dive right into it. As you're very well familiar, there are these, loosely speaking, two approaches, two camps, two schools towards GR. On the one hand, the relativist approach, and on the other hand, the particle physicist approach, and maybe to speak sociologically. Sometimes you would associate A with a geometrical viewpoint and B with a more field theoretic viewpoint. But of course, this is up to discussion. I guess, especially we here don't all fully agree with such a straightforward distinction. I think a very nice detailed account of these two approaches, how they benefited from each other, and how they could have benefited from each other, is given in various papers by Brian Pitts, who I see delightfully also joined us here today via Zoom. And so, please have a look at the reference later for more on this. I want to jump right into it with some typical textbook statement, as I would think, with respect to the spin-2 approach towards relativity. Here is Klaus Kiefer in his continuity textbook on what I would describe later as the self-interaction approach. So just take a spin-2 free field theory as represented by the Fields-Pauli Lagrangian. And then if you look at it, the question arises, so Kiefer asked whether it could serve as a candidate for fundamental helicity 2 theory of the gravitational field in a flat background. As it stands, it's certainly not possible because, as already mentioned, because one has a certain kind of problem of consistency with the energy momentum conservation, holding on the one hand at the same time now the matter being asked to interact with the spin-2 field. Man might thus wish to add the canonical energy momentum tensor to this whole thing with respect to the H field, and then from such a modified equation, one would think one would get towards some better behaved equation. But the problem here really is the story continues. You need to add more and more corrections, and this will lead to what we could call the self-interaction approach. And just next to it, without conflating it maybe, but still kind of putting it directly in vicinity, Kiefer mentioned some approach by Boulanger et al., which I will take here to send in representatively for the so-called gauge deformation approaches. Boulanger et al., he writes, have shown that starting from a finite number of Fields-Pauli Lagrangians, no consistent coupling between the various helicity 2 fields is possible if the fields occur at most with second derivatives, leading only to a sum of uncoupled Einstein-Hilbert actions. So if we take a quick step back, whereas the self-interaction approach is about how you derive step by step, or allegedly how you derive step by step from the Fields-Pauli equation, the field equations, including the Einstein-Hilbert action. The result by Boulanger is presented as more of a restrictionist claim, given certain kind of constraints. You will end up with the Einstein-Hilbert action as the only possible generalization of Fields-Pauli. Working out exactly what the difference between these two is and why these two viewpoints on the spin-2 approach towards relativity shouldn't be mixed up will be one of the goals of this talk. But maybe step by step. So let's zoom out for a moment. Here's an overview to the particle physicist approach. So simplistically speaking, again, the relativist approach might be associated to the. Sorry. Okay. Okay. Simplistically speaking, the relativist approach might be again associated with the geometric viewpoint. And the particle physicist approach branches up now into a classical and a quantum route. On the classical side, we have these so-called self-interaction approaches, as was mentioned already in the first quote from Kiefer, championed by people like Gupta, Kreitman, Feynman, Deser, nowadays maybe Barcelo, Pitts also. And on the other hand, we have the classical side, the gauge deformation approaches, Fang and Fronstal, Hinault et al., etc. If you want, you can also count Weinberg's work in this context as part of the particle physics approach, works on the S matrix and how the S matrix allows you to derive, S matrix formula allows you to derive things about the principle of equivalence, universal coupling, but definitely could also be seen as a way of shedding light from the particle physics route onto GR. Okay, what I'm interested in today is first of all the self-interaction approach, and then I want to guide you from the self-interaction approach to its proper understanding, which will culminate after all in the gauge deformation approach. Here's an attempt at the first characterization of the self-interaction approach. The self-interaction approach takes it that GR can be derived in flat spacetime based on a sourcing of the massless spin-2 field equations by energy momentum. I put on purpose derivation, flat, and energy momentum in italics, because these are these three things which need to be discussed here, which are actually highly controversial, and which will ultimately be the decisive factor as to whether this claim is true or not. Okay, for this talk, we will fix the seventh action approach to be concerned with a flat spacetime background. There's a lot of differentiation you could make what a flat spacetime background really means. Brian Pitts has great work in this respect. So have a look at his 2016-2022 papers for a more sophisticated take. What I will focus on today now is this role of derivation and energy momentum tensor. What kind of derivation do we have to are we dealing with in the seventh action approach? Yeah, and how much does this relate to the energy momentum tensor? So this will be the focus of our critical discussion here. Philosophical claims which have been made recently in the context of the seventh action approach are, for instance, that by Salim-Khani about a supposed ontological reduction of generativity, or sector of generativity at least, by the spin-2 approach that is then cast by Kian, a friend of mine, in the context of the spin-2 approach. And if I understand correctly, then Kian has already presented his work here in this audience, so some of you might be familiar with it. So this can be seen as, in some sense, as a continuation then. And okay, going a bit further back, in 2018, Feynman, brought us this tale of Venusians, particle physicists, were wondering about some attractive force they've come across and actually begin to model it within their already given particle physics framework. So the story of the famous Venusians from the 1962 lectures is that you mentioned successful particle physicists on Venus who discover a new, very weak attractive force. And then, since they are particle physicists, they might be able to just simply add one more field, so the story goes, and find some consistent dynamics to it. So this is a story of how someone who already knows particle physics allegedly could arrive or could have arrived at generativity, right? And here again, the glimpse on what is meant by ontological reduction in the context of the self-interaction approach. We have Kian here writing, spin-2 theory provides us with a non-geometrical derivation, so stress on derivation, of the Einstein field equations, and can be understood as a fixed field formulation of GR. And then that reduces, so stress on reduces, GR to a special relativistic theory of an interesting massless spin-2 field. Of an interacting massless spin-2 field. And then getting more ontological, put in terms of the famous God metaphor, if God had created a Lorentzian spin-2 field and the other Lorentzian matter fields, she would have created a world described by generativity, with G as the effective metric field. Okay. So maybe let's think for a moment. So this is really a claim based on some form of theoretical reduction, which is then also understood as a form of ontological reduction. The claims we will put up now are the following. So first of all, maybe not innovatively, but just more of a reminder, the self-interaction approach doesn't provide a derivation in a straightforward logical sense, as it is plagued heavily by ambiguities. To be the first point. Even if you think that the derivation is not needed for a view of a GR's metric field as a mere stand-in for a self-interacting field in flat spacetime, we argue that there is a dilemma arising. So that will be the second part of the talk, exploring this dilemma. And then on the positive side, the point will be that the self-interaction approach should be rather understood as a way towards a gauge deformation approach, and thus not as a form of reduction of GR to particle physics, but rather as a clearer account of the structural features of GR's metric field and GR with respect to its perturbative expansion. So, derivation of GR, a dilemma for the self-interaction approach, and then towards the gauge deformation approach. So what is the self-interaction approach step by step? In our most charitable reconstruction, we assume a classical spin-2 field, H, with its typical equation of motion, Fierce-Pauli equations. So we have G equals to 0. G is the equation left hand side of the equation of motion for the free field H. Now let H universally couple to matter other than H via its matter energy momentum tensor. So via the energy momentum tensor with respect to all matter other than H. This brings us to the already aforementioned consistency problem. So might have been a bit quick in the quote from Kiefer, but here we see it now spelled out. On the one hand, T is not conserved. Since, well, the matter on its own would be conserved, but since T now interacts with H, it won't be conserved. Okay. On the other hand, though, this object is still the same as for the free field theory, and that is mathematically conserved. So identically conserved. So on the one hand, T is not conserved, on the other hand, T is conserved. Natural reaction is, well, we have forgotten within this T the contribution from the H field. So we start adding a small t, T0 call it. Okay. But then we run into another problem we could call the methodological consistency problem. The energy momentum contribution from H, which leads to T0, is part of a new equation of motion sourced by T. Namely G1, G0 minus T0 is equal to big T. And again, we have to now ask, what is the energy momentum little t with respect to that object, and have to add this on top, and so on and so forth. And we have to do this, of course, also at the n+1 step, right? And so we end up with an iterative relation. And so we add all these little t's, and then the claim is if we either at some point for some n, t becomes 0, or we have taken the limit n goes to infinity. And then ultimately we can replace eta plus h in our expressions by g, and we end up with the Einstein field equations. So, or in a similar way goes the story of the self-interaction approach. Is everyone bearing with me here at this point? Or okay, good, yeah. Now there are all forms of ambiguities involved here. Some less unexpected, some more unexpected, some less harmful, some more harmful. So surely we have a question of with what kind of spin-2 fields to start with, right? Traceless, not traceless. And for instance, according to Barcelo, the traceless H field would just lead to a volume element, which is equivalent to volume element of Minkowski spacetime. So you best reproduce unimodular gravity. You don't get full Einstein gravity. Well, when you ask a question for the equation of motion, you could wonder why restrict yourself to the second order. However, at least at second order, the Einstein, the Fierce-Pauli equation are kind of the unique Gaussian invariant equation. So that seems more or less a natural choice. It becomes more severe when you get to ask what does it really mean to source your free field by matter, even universally. What does it really mean? And we come to this in a moment. And of course, the question really, which really gets the fight started in the community is, or in the critical literature at least on this, is what do you mean by energy momentum tensor here? What kind of t, so little t, so to speak, is used? What kind of prescription is used? Is there at all a prescription? And yeah, if you have a derivation with these ambiguities, at least prima facie doesn't look like a straightforward derivation, at least not a derivation how you normally get from one theory to another theory in the context of reduction, let's say. But okay, let's see. Consider, for instance, the choice of meta coupling. What exactly is the physical picture? Is the physical picture that of self-sourcing at the level of the equation of motions? So yeah, as you're familiar, the left-hand side of the equation of motion gets T as a source, or is it one of self-coupling at the level of action, right? As particle physicists like to talk. So something like H times T. Well, in any case, these choices are not equivalent. So self-interaction and self-coupling are not equivalent because, well, if you derive the equation of motion with respect to H, you take the variation of the H times T term, you don't just get T, but you get T plus H times the variation of T with respect to H, which is different from just saying the source is just T, right? So and so on and so forth. Just, I mean, this was pointed out by Linnemann. Maybe there's some way to go around it. Just this is something which needs to be dealt with. Apart from these ambiguities, there are also some form of oddities and restrictions of this spin-2 approach. An oddity is that the self-interaction problem seems on the one hand motivated from inserting external matter. So that's how the whole problem got started, with having this big T on the right-hand side, so to speak. But all the accounts we are familiar with, they actually then idealize this big T away with. So that might be okay. I mean, after all, you would say, why should the derivation of gravity depend on the specific matter content you have? Why should this matter? That might be an idealizing assumption, is okay, but no one explicitly actually works with the big T still there. And more seriously, maybe there's a problem. If you start with a certain kind of big T for the matter other than H, which is defined relative to Minkowski background, how do you conceptualize the actual the arisal, or how do you even get the arisal of the meta energy momentum tensor as you're familiar with from GR? That's something which is just, to our knowledge, not spelled out in the literature at all, and yeah, at least fully underexplored. With respect to limitations, many things could be said. Linnemann again has this point about that allegedly you cannot reproduce the right surface term, so you might be able to get the field equations, but not the right action. But of course, you can also argue and wonder about what is the value of the action. And of course, there might be other actions which are much more favorable than the Einstein-Hibbert action for considerations of energy and so on. So it's something I could go into detail with, but let's just keep it there for the moment. And then, of course, there's always this long topic of topological restrictions and causal restrictions, which are arguably connected, right? So with respect to topological restrictions, you might say this global flat background in some way or another restricts you to spacetimes homomorphic to Minkowski spacetime. But I think this is this can be really really discussed with. In any case, it seems rather unproblematic if you just use this method as a local method. However, that might not be the way to look at it if you really want to do an ontological reduction, right? There's a third way, I think, just take the Minkowski metric not as a background spacetime as such, but read it more in the spirit of a numerical metric. That's something proposed by Brian Pitts. So there are ways, again, to deal with these things. It's just something which sticks out again and might keep you worrying if someone just calls this a derivation, right? On the level of causal restriction, I think interesting result, of course, by Pitts and Schief about that if you require the G metric to be in agreement with the causal structure, background structure of the Minkowski background, then you restrict your G effectively to a global hyperbolic spacetimes. So it's also, I think, an interesting result here. So take it as a plus, so take it as a minus, but this would be one of the restrictions here.
Niels, can I ask?
Oh, yeah.
It says third way.
Yeah.
Does it mean that if you have the Minkowski metric as a mere numerical metric, you in some way get over topological restrictions?
I think so, yeah. I think so. That's the idea, yeah. Because your notion of what you mean by eta just becomes much lighter, and therefore certain commitments you have normally with a fixed eta in terms of additional gauge group or gauge group constraints in terms of coordinate charts and so on. This all somehow disappear because you don't understand you don't think of the eta as really a spacetime anymore itself. I have to say I cannot really explain the details here, and this is something I have not looked at. But maybe we can discuss later. It would be But this would be the rough idea, yeah. Good. Just a question with respect to time.
I think we started the course later.
Okay, good. Okay, good. Thank you. Yeah, and of course there are further issues. How does the replacement G equals H plus eta really work? Even if there were no ambiguities or harmless ambiguities, could you really carry it out, so to speak? It's also, I think, an interesting epistemic question. Could you really do it? Could you really start at the beginning without knowing the result and really get to the Einstein-Hibbert action or to the field equations, and so on and so forth? Okay, so there might be no derivation in a very straightforward sense, but you could say, so what? One might take an unambiguous derivation as inessential for a self-interaction view of GR, right? A view on which simply that the GR's metric is meant as a stand-in for a self-interacting field in flat spacetime. So arguably the particle physicist's take on gravity is just much better explicated by this view anyway, right? I mean, so what you really mean is not that you can derive in a strict sense the field equations from this linear equation through some self-coupling, but you should understand the G metric as an effective stand-in for a self-coupling interacting H field, something like this. Yeah. Okay. And a dynamic approach to relativity could very well work with such an attitude. So in contrast to the proposal by Kian, it seems sufficient to just use such a self-interaction view as opposed to a self-interaction derivation. Okay. We will now present, however, a dilemma for proponents of such a self-interaction view of GR. Whether it convinces you, we will see, but I will try to do my best. And I have to say, I present a bit much maybe in a black and white fashion. That's why I call it here also a simplified dilemma, but maybe this also gets us into a nice discussion later on. So the dilemma is as follows. Either you insist that there is a sourcing of H by some kind of proper physical energy momentum tensor. Then, however, we will argue the self-interaction dynamics is not satisfactorily interpreted without making recourse to a curved background spacetime. Or you insist that there is simply self-interaction of H. So it is this interaction of H with itself, simpliciter, so without having to bring in a notion of energy momentum tensor. Then, so the argument will go, there is no good reason anymore to interpret the self-interaction relation dynamically. So we end up with more like a structural relation. Sorry, this is double. We end up with some structural account. So the relation rather has the status of, and as we will see, of a formal perturbative expansion of many with no good grounds for preferring or singling it out from others. That will be the argument. I mean, so again, either think H couples to the energy momentum tensor, but then, yeah, what really is this energy momentum tensor? You can only really make sense of it by, after all, making recourse to curved background. Or if you just drop the idea that you need some coupling to energy momentum tensor, the point will be, well, then there's just not enough physical significance in this relation anymore. It's just a structural relation as you have it basically with all forms of expansions. Okay, that will be the argument. You are still bearing with me here? Okay, good. Yeah, good. So to the first horn. So which energy momentum tensor to take anyway, right? So as you know, I guess energy momentum tensors are ambiguous with respect to additions of superpotentials, so terms basically which vanish if you hit them with a divergence mathematically. Yeah. Okay. And also in this context specifically, we have the problem. The standard notion of related energy momentum tensor is not symmetric here. So, however, the sourcing requires a symmetric energy momentum tensor. Interestingly, if you were using the self-coupling approach as opposed to self-interacting, so at the level of the action, yeah, you could basically couple the H to a T, which is not symmetric because the unsymmetric part would just disappear. So you can discuss. But we are working at the level of the equation of motion for the rest of this talk here. Yeah, and also a valid sense of energy momentum tensor should actually exist at each step of the iteration. So at best you have a prescription so that you can systematically always adhere to the same sense of energy momentum tensor, or otherwise a brute list of EMTs for each step. But you need some account, not just at one step, but for all the steps. And so yeah, at the end of the day, you won't probably get around a prescription. And the standard prescription, which is put forward in the literature, let's say if we look at Barcelo, for instance, I think one of the more current or most current, really in detail reconstruction of the self-interaction approach, really trying to get to come to grips with it. I mean, he does it more for unimodular gravity, but basically things would carry over. So they claim to gravity itself, to Einstein gravity itself. Okay. So what you have here, well, okay, maybe this also goes on other names, but let's call it a Hilbert prescription. So choose the action for the n spin-2 equation of motion, generalize this action to curved spacetime, apply the Hilbert prescription, and then restrict to flat spacetime again. And then yeah, you can of course argue also about the minus sign, the 1 or 2 here, and so on. But yeah, and also there's some ambiguities. Yeah, how to trigger the action when you have this like finding the integral, right? And also how do you generalize curve space and also ambiguous? At least you can reduce it into one ambiguity or so. Marcelo will argue because you can shift between these two. That's kind of at least a nice result here. In any case, let's ignore the ambiguity to just stare at this object here. What is this? Oh, sorry, I should have. Let's stare at this object here and ask what this is. Well, certain voices, for instance, by Deza, or here we have Marcelo et al., say, well, it is only a mathematical prescription to obtain a symmetric version of the canonical stretch energy tensor without special physical content on its own. It's just a tool, and period. So, good. That's where we start to disagree. So, okay, in the context of spin-2 in flat space, it's true. The Hilbert prescription does pick out a symmetrized Noether energy momentum tensor. So it's nice. That's a good result. There are contexts of other theories in flat space time, though, where the Hilbert prescription does not pick out the accepted Noether energy momentum tensor. Take, for instance, linearized Gauss-Bonnet. The accepted Noether energy momentum tensor there is symmetric engagement variant, but it's not equal to what you get when applying the Hilbert prescription. Okay, and more generally, you can argue that yeah, due to terms you get from especially from higher derivatives, you will always have a different result for the Noether energy momentum tensor, which is symmetric with maybe with a Hagen construction even, and it will always be different from the Einstein-Hilbert action. From what the Einstein-Hilbert prescription gives you. Oh, sorry, put more simply, at some point, that the Hilbert prescription picks out the symmetrized Noether energy momentum tensor is just not true anymore. It for certain more general theories of higher curvature gravity, let's say, you don't get for the Hilbert prescription the symmetrized Noether energy momentum tensor. Good. And this seems to shatter, I don't know, at least for us, confidence in the Hilbert prescription has been two contexts as well. It only seems to derive, I mean, the only reason why we use it seems to be rather, again, now, because it works. I mean, if it doesn't universally work, but just works here, then after having seen that, so to speak, and updated our knowledge, so to speak, we should think, oh, now, unless you give us a new explanation why it works, it just seems to work because it works. That's the reasoning here. On the other hand, you could make the case, okay, at least, okay, we have a specific Noether energy momentum tensor, think about the Hilbert prescription, but it's not definitionally dependent on the Hilbert prescription. You can also just arrive at it at doing the canonical energy momentum tensor and improving it with superpotential, so you can independently define it, and that's good at least. But the question, of course, remains: how attractive is this view? Because there are infinitely many energy momentum tensors. Okay, so again, you could say positively for this self-interaction view. The self-interaction view on energy momentum tensor fulfills the minimal requirements for ontological grounding story. So yeah, you do have like in your collection of what there is, you can have, you say you can pinpoint at one specific symmetrized Noether energy momentum tensor, and if you put this in, then it somehow seems to work with the self-coupling relation, ignoring now other ambiguities. But just to put it very simply, how does the H field know how to couple to that EMT specifically? I mean, that seems quite arbitrary and unsatisfactory. On the other hand, the take on the relativist view seems straightforward. The way how you define the energy momentum tensor and what grounds what is also is aligned, right? The Hilbert prescription for matter is fundamental, so to speak, and from that you get also your local sense of energy momentum tensor in the flat case. Good, and we could argue about this, but this is, so to speak, the first horn. And summarized like this, maybe a bit too drastically, but as I said, black and white a bit. So the curved spacetime setting guides our choice of the correct T, but it seems worse. The attractive physical interpretation of T is from the curved spacetime setting. Okay, second horn. One might take the mere existence of a defining recursive relation, however, as sufficient to establish that GR symmetric field is a mere stand-in for a self-interacting field in flat spacetime. So you might just say, we don't, I mean, the dimensional tensors are just like always, right? They're nice to have if they're the right symmetries, but we don't need them to do physics. We can do physics just immediately with the field themselves. But then take a look at this. I hope I didn't do any mistake here because this I had to correct last minute. So if you have a expression like xx minus 1, and yeah, you can explain it, of course, like this here. Then you can also write this as a recursive relationship, right? Where you say fn plus, difference between fn plus 1 and fn is basically some prescription applied to fn, which doesn't depend on the n. It's just something which takes an f and gives you some other term out of it, right? In that case, yeah, just multiply your f as an x, and then divide this by some maximum value for when this derivative is still unequal to 0, and add a 1 there, something like this. And as you hopefully agree, this then reproduces our f infinity here. So there seems to be nothing special about the function or functional, so like the functional g of g or the function x of x can be re-expressed as a limit of a sequence whose elements then in a recursive relationship. It doesn't seem to be anything special. I mean, the structure, it's not like you can say, even though you forget about the physical coupling to an elemental tensor, this relationship itself, this relation itself is still wholly also. Or that's at least what we would like to point out here. So the argument runs as follows. Without a dynamical mechanism as coupling to energy momentum in terms of which to understand the self-interaction recursive relation, the relation between sequence elements g of n and the limit to the sequence g infinity is merely structural. So, okay. And then, and this might be controversial here, if a relation between sequence elements and the limit to the sequence is merely structural, the sequence limit is prima facie fundamental, and the sequence elements arise from its perturbative expansion. Compare, this would at least be our intuition for the X case, and so I would think generalizes also for other cases. Thus, the sequence limit g of infinity is prima facie fundamental, and the sequence elements arise from its perturbative expansion. So if you would talk in terms of best explanation, it seems the best or the most natural explanation in this case is really like we would give for X. So we should give a similar explanation for the G, yeah, for the recursive relation with respect to Gn. Okay, now we end up basically thinking of spin-2 as a perturbative view of GR with respect to a specific background, namely the flat background. But of course, we can ask this usual old question asked a lot in the context of when we're quantizing out of flat spacetime. Is there a reason to prefer the flat spacetime expansion over some other perturbative view or the non-perturbative view, right? That's something. And then we come in with a Jewish interest in super empirical virtual comparison. And there we would argue on all kind of different categories, the non-perturbative view scores and not so much the perturbative view, especially if just taken on its own with respect to Minkowski spacetime. So the non-perturbative view unproblematically reduces the perturbative view, but not vice versa. We've seen it at the beginning, that the derivation just runs in one way, not the other way. Non-perturbative view has a wider scope of applicability. Could be also a bad thing, who knows? And this is stronger, I would say. Non-perturbative view is more parsimonious in its assumed structures, could also be discussed. But yeah, I think this point seems to make it pretty clear as well that since the reduction relation anyway seems to just go from this one side to the other side. And since really the non-perturbative view seems to be like the common core to all this different fragmentist perturbative expansion, why take one specific perturbative view as special? And what has been argued, for instance, by I'm studying from Gupta, but also up to Kian, is of course that, yeah, in some sense, what's nice about the flat spacetime background is that it offers prospects towards a form of unification, and fair enough. But I think at the moment we have kind of moved on where we just say, okay, Minkowski based spin-2 is an option, but it's just one out of many complementary EFTs we have. There's nothing wholly about this anymore that we need to quantize around spin-2 further. And yeah, for people who are interested in that, I think I can recommend also chapter 9 here of Huggins and Ritchie's book. Okay, and now I'm not exactly sure anymore what I wanted to say with the Pitts reference here. But I think, again, if you have a more sophisticated view of what you mean by the eta, then yeah, this doesn't apply to you, so to speak. This, I mean, as Brian writes, I think, yeah, taking the eta as a numerical matrix is basically very close to GR still. It doesn't have this taste of a background spacetime here. Okay, but maybe we can discuss later. Okay, so what do we do then? So positively speaking, if you accept the dilemma, I can still offer something why the self-interaction approach is worthwhile. The way in which the self-interaction approach is worthwhile is that it can be seen as a heuristic ladder towards a new way of looking at the structural relationship between GR and yeah, one of its limits, so to speak, yeah, the special relativistic context, so to speak. And this is cashed out in this gauge deformation approach, Fang and Fronstal, Wald, Boulanger et al., and so on. And we will see this yet now here. So, so just work now at the level of the action to express the G of i's with some action F. And after the rewriting, what you see is that the consistency problem basically retransforms into a problem of deforming. So this is about transformations here. Deforming the original gauge transformation of flat spacetime, of the flat spacetime gauge symmetry of the H field. So the H field has a gauge symmetry associated to it, and trying to and re-expressing this, re-expressing the consistency condition in terms of these actions leads to actually to a way of understanding the consistency problem as a problem of gauge deformation. So solving the consistency problem is equivalent to finding the extension of the gauge group under this deformation. And then, of course, you get very natural into your models of not so much looking for unique derivation, but just looking for sufficient constraints, such as these constraints will entail that only one possible generalization is possible. Only one possible, yeah, only one deformation is there, so to speak. You're eliminatively reducing the options there. So again, as Wald, for instance, stresses quite explicitly, there is no unique derivation here at play. There's a lot of branching points, so to speak. But nevertheless, the gauge deformation approach is attractive as it showcases the structural relationship between one theory to another in terms of gauge group, by doing so without this problematic idea of energy momentum coupling. So we go to a more mathematical point of view, so a bit in the sense of the second horn. But yeah, rather than think of it in any form of dynamic interaction, the picture is now just the group theoretic picture of gauge deformation. Yeah, so the consistent problem is kind of recast as a problem of gauge deformation, not of dynamic coupling. And here we see now, for instance, Boulanger et al. As a state-of-the-art result. So under certain assumptions, locality, point covariance, a sum of independent Fierz-Pauli actions, certain spacetime dimensions greater than 2, as a limit for free field, and at most second-order derivatives. Then the only form of extensions we can have basically are Einstein-Hilbert actions or Fierz-Pauli. I mean, basically nothing happens then. But so this is just a sum over all kind of different Einstein-Hilbert action. Okay, plus cosmology constant, and that's the way how you should understand, so to speak, the consistent problem recast as a problem of gauge deformation, and then you get all these nice, clean and unproblematic technical results like this here. Okay. So in sum, we can say the self-interaction approach does not provide a non-ambiguous derivation, nor can it more generally support a view of GR, according to which GR's metric field is a mere stand-in for dynamically self-interacting field in flat spacetime. But it has led us to a view of GR as a gauge deformation. And the gauge deformation view provides really a structural understanding of the relationship between linear gravity and GR. And yeah, just to sum up, it doesn't have more, but also not less with interpreting GR than, say, other intertheory relationships for instance, to Newton-Cartan theory does. Okay, thank you.